Assalamu alaikum. Welcome to the first lecture of chapter 11. As you can see, the chapter is about the material category known as ceramics. As we introduced in the beginning of the course, the major categories of different materials are metals, polymers, ceramics, composites, and so on. So we have covered metals in a lot of detail. We have covered polymers to some extent. And now this is the type of materials which are known as ceramics. I will skip this slide. This just addresses in this chapter what are the types of things we will cover. So we will go to the next slide. Now, ceramics are inorganic materials and non-metallic materials, right? They are non-metals, of course. Inorganic, organic materials and inorganic. If I ask you what are organic materials, what would you tell me? If you are telling me that they are mostly carbohydrates and carbon hydrogen type of compounds and so on, organic, then you are right. Right? The word organic originally is because these materials were discovered in living organisms, human beings, animals, plants, and so on. But later on, it was found that many of the organic materials, carbon hydrogen chains, polymer type of chains, are also there in oil derivative materials and petrol derivatives and so on. So those are also called organic materials. Inorganic are the other ones. If they are not polymers, if they are not carbon hydrogen chains, then they are inorganic, right? And as you can see here, they are generally bonded together by ionic or covalent bonds. So this is important. You see, they are not metals, that is one thing. And then they are not polymers, but it means they are compounds. It means because if they have either ionic or covalent bonds, then they are not simple materials, but they are compounds. So yes, this is important that ceramics are inorganic, they are non-metallic in nature, they are compounds, and the bonds can be ionic or covalent. Of course, this you may know from your earlier courses also. Their general properties, they are good conductors, opposite. They are good insulators of electricity and heat. They don't, right, they are not good conductors, so they can be used as insulation. Other very important property that they are very hard and brittle. I have discussed a lot when we were in chapter 6 about material properties, about the difference between hard and brittle. Hardness is related to strength. If something is very strong, it will be very hard also. Brittle is something else. If it is not very ductile, then it will be brittle. So brittle does not mean whether it is a strong or not. A less strong material can also be brittle. A very high strength material will also be brittle. So as long as ceramics are concerned, they are very hard, so they will be very strong. But they are brittle, it means that their ductility is small. So ductility and toughness values are smaller than metals, even though their strength is very high. Then chemical stability is very high. It means that they do not react with other materials easily. So this is a very good property. And they have a very high melting temperature. This is their most important property, that their melting temperatures are generally even higher than metals. So they are high temperature resistant, right? So this is a general background of what are ceramics. Traditional ceramics, clay, silica, sand, and those things. And from there, glasses, bricks, construction tiles, the porcelain used for electrical applications. These are ceramics which are traditional ceramics, right? When we say construction tiles, then in your houses, the tiles used on floors and sometimes windows and so on, right? But then these are traditional ceramics. Engineering ceramics are also complete ceramics, same type of properties, but they are non-traditional. They are being used in applications which are not generally these. So alumina, silicon carbide, silicon nitride, these are some of the new ceramics which are known as engineering ceramics. We will study about more of them. Now here is a table. Here is a table, right? So we are talking of the covalent bond and the ionic bond. You know, if the electronegativity difference is small, then things form covalent bonds by sharing of the electrons. But if the electrons completely transfer from one to the other, then you form ions, a positive ion and a negative ion, and then ionic or electrovalent bonds are formed. So both types are here, and that depends, as I just said, on electronegativity difference. So here is a table of some famous ceramics: zirconium oxide, magnesium oxide, aluminum oxide, silicon nitride, silicon carbide, some very famous. And these are the bonding members, of course: zirconium and oxygen, magnesium and oxygen, and so on. The difference in electronegativity: 2.3, 2.2, 2.0, 1.7, 1.3 points, right? So high electronegativity difference. Without going further, we can say that these will be electrovalent bonds, and these will be most probably covalent bonds. So therefore, you see, percent ionic character, how much percent are they in ionic? 73% chance that they will form ionic bonds, and only 27% chance that they will form covalent bonds for zirconium oxide. But if you go to silicon carbide, where electronegativity difference is only 0.7, only 11% chance that ionic bonds can be formed, but 89% chance that covalent bonds will be formed, right? So mostly silicon carbide will be a ceramic which is covalently bonded, and mostly zirconium oxide or zirconium dioxide is a ceramic which will be electrovalently or ionically bonded, right? So this type of chemistry we can see. Generally, of course, you know that if a bond is covalent, it is not as strong as if it is ionic, electrovalent, because electrovalent, so those things are there. Now here we want to show you, we are showing you the different columns of the periodic table, and we take some examples, I mean, of the same two type of things, that are they covalently bonded, are they electrovalently bonded. So let us proceed. Right, so you see, we are talking of the ceramic called calcium fluoride. Calcium fluoride. Now calcium is here in only column 2A, and fluorine is in 7A. You know that there is a huge amount of electronegativity difference if the columns are different, right? So this calcium 1 and fluorine 4, so a difference of 3. So this is a huge difference in electronegativity. Therefore, calcium fluoride will be a ceramic which is formed by electrovalent or ionic bonds. Let us proceed further. Take an example of silicon carbide that we did earlier. Now both are in the same column. This is 2.5, this is 1.8. So the difference we know, we saw from the previous table, is only 0.7. So compared to calcium fluoride, where the electronegativity difference is 3.0, here it is only 0.7. So again, silicon carbide, right, will be there, and a ceramic will be formed, but it will be much lower. So going back to the definition now, if you see calcium fluoride, silicon carbide, so it is not just that they are, I mean, metallic, non-metallic materials and so on, but usually they are formed between one metal and one non-metal. Calcium is a metal, fluorine is a non-metal, silicon is a metal, carbon is a non-metal. So usually they are formed by making compounds between a metal and a non-metal, right? Now just for fun, I mean, so that I always want you to realize that in the real world, where do you do all this material science that you are talking about? So have you heard of silicon carbide somewhere? You try to think. Have you heard of silicon carbide somewhere? I don't know. But you see, all of you have done workshop, right? Lathe machines, milling machines, and so on. So the cutting tools that are used, cutting tools, are made from special materials which are tool material. They are called tool steels because their hardness is much more than normal steels. Why? Because the cutting tool hardness should be much more than the steel we are cutting. Only then we can cut it. But then how do you cut tool steels themselves? You see, tool steels are very hard steels. So you use tool steels to cut normal steels. But if I want to make the cutting tool itself, then what material should I use to cut this? This is already very hard. So silicon carbide is a ceramic. Its strength and hardness is much more than metals. We know that. So we make a small tip, only a small tip of silicon carbide and put it on a normal cutting tool. Now it is a normal cutting tool, but the tip is made of silicon carbide. And this silicon carbide is much harder than even tool steels, right? So silicon carbide is one of those materials which is used in cutting tools and so on. Okay. Where have you heard of calcium fluoride? Where have you heard of calcium fluoride? If you remember, go to any toothpaste. They will tell you that it has been fortified or strengthened with calcium because your teeth are bones and calcium is a very good material to increase the strength of the bones. Also, many toothpaste will tell you that they contain fluorine or fluoride toothpaste because they are very good for your dental health. So calcium fluoride is a ceramic, but it will be used inside toothpastes and so on, right? So I try to do this to you only so that you understand where these materials are being utilized in your normal world, right? I keep on telling you that doing a course is important, but as engineers, we should always think of the applications. Okay, let us proceed further. Simple ceramic crystal structures. Simple ceramic crystal structures. So here the more traditional ceramics are given in two parts of the table. Hafnium carbide, we are starting from here. Hafnium carbide, titanium carbide, tungsten carbide, magnesium oxide, and so on. And these are the melting temperatures. Just see 4000, 3000, 2800, 2800, 2700, 2500. We have told you that steel, which is a very strong material, melts at 1000 Celsius, 1400 Celsius, 1600 Celsius, and so on. So these are all 2500 melting temperatures and above. And then the second part of this table, boron carbide, aluminum oxide, and so on. And so they have arranged them in decreasing melting temperature. If you see decreasing melting temperature, but even titanium oxide is 1600, which is more than most of the steels and so on. So therefore, you see, this is very, very important that ceramics are very high temperature resistant materials. So now, before going further, what is the major use of ceramics, right? Now, we have been talking so many times that how do we make metals? We go to areas where iron ore is there. We do the mining. We take the iron ore, we crush it, we make it into a powder, we melt it. And after melting, we do the chemical reactions and so on, and then steel is formed. But where do we melt it? If the furnace is made of steel and we want to melt iron in it, the furnace will also melt. So you see, you have got the answer now. The furnace will be lined with ceramic. So the ceramic can melt at 4000 Celsius. It will not melt. But at 14, 15, 1600, all the iron and steel will be completely melted. So whenever you want to do metal industries, then you do them here. We will take a small break here.